Welcome everyone to this new episode of the Water Underground Talks. And it's my great pleasure to welcome Professor Joanna Doummar from the American University of Beirut. So Joanna, how did you first develop your passion for water?
First, thank you for having me and for the opportunity. I'm very happy to be here. So my passion for water goes back to way ago. So it all started with BS in geology. But then I still found geology a little bit dry. So I went on and pursued a master's in reservoir characterization. And then I still found it a little bit dry still. So, but then I had the opportunity to work in a consultancy firm. And then where we did a lot of projects related to hydrogeology and lots of fun experiments. And this is when I fell in love with groundwater and hydrogeology. So basically, this was my incentive to go and pursue a PhD in hydrogeology in Germany, specifically in Karst hydrogeology. And then and since then, it has been a very long love story.
Wow, that's very interesting. So the second question we have for you is how does your personality, or how do you think your personality or personal interests make you a better scientist?
Well, actually, the first thing is that I'm a very creative person, so I'm very intuitive. Somehow I like to write. And on the other hand, I'm a very quantitative person, so I'm very keen on finding evidence to support any hypothesis that I have. And just if you mix these two, I mean, this makes a very good recipe for a scientist, in my opinion, where one could develop ideas that are outside the box, where we can imagine the unimaginable, and then still try to look for evidences and proofs in order to be able to really produce science. So basically, these are the two aspects of my personality that makes me this scientist I want to be.
Yeah, as you say, it's a very interesting recipe, and we can see the impact also in your work, as we are going to see in a bit. But before continuing, one last question. It's a curiosity, which is, what is the impact of your work outside of academia?
Okay, so basically, I mean, as we all know, water is something really important besides being a research field. Uh, so, uh, so basically, whatever work we do, uh, in addition of being something that we would like to publish in international journals and basically look in details at some aspect of groundwater pollution, etc., our work and the work of any hydrogeologist has a developmental impact, where basically we are able to help local communities in providing the sustainable use of groundwater, etc. So just to give you an idea, like for instance, we do high resolution recording of spring data and climate data on pilot areas. And basically this data is shared with water establishments so that they are able to secure the sustainable water resource and to find basically alternatives in case they have predicted some decline in groundwater resources. Another thing is that we always try to convey all of our results in technical and non-technical workshops to stakeholders and local decision makers. And for instance, if we develop a model, we go with this model and present it to local stakeholders so that it has a bigger impact and that they can use it actually. And basically, at the end of the day, I mean, all of our work can be translated into policies and as decision tools so that, I mean, we can help, especially in developing countries, for good management of groundwater resources. So, yeah.
Well, thank you. It's very interesting and very inspiring also. And I think we are all even more curious to know a bit more about your work. So if you would like to share your presentation with us, we would be very happy.
Thank you, Viviana. Thank you very much. Thank you, Viviana. So basically today, um, I'm just going to ask the question, why Mediterranean and why semi-arid? What is so specific about these climatic conditions? So first of all, future climate variability has shown that we have a high variability and variation in the future, and this will pose some constraint on water resources, basically. And only if we can conceptualize the flow and transport of these water resources and know the relationship between input and output, that we are able basically to achieve better sustainable management plans and preserve the groundwater at the source. So why karst? Because I mean, karsts are very challenging. I mean, they're the most difficult aquifer system to conceptualize because they're both heterogeneous and complex. So basically, they have, as you can see on the picture, they have this duality of infiltration and flow, where water infiltrates in point source, such as dough line, and it infiltrates in a diffusive manner as well. And below the ground, it also flows in conduits and in large fractures, and it flows in small pores and fissures. So this makes this duality a little bit very difficult to conceptualize. And as we can say here, that they are also very high vulnerable to pollution, because if we're talking about flow velocities that can reach up to 100 meters per hour, then it is very difficult to be able to treat the water in due time. So what are the basic challenges and threats in karst systems nowadays? So especially in these areas, semi-arid and Mediterranean, where we have uh, mild winters, where we have a certain level of precipitation, even in snow-governed areas. But on the other hand, we also have some dry summers, very dry summers. So basically, where we have high overflowing springs during winter times, we have also a very high deficit during summer times, as you can see on both pictures. And if the urbanization and the needed demand is to increase, as we can see here on the red graph, on the red curve, we can see that at one point in time, we will be unable to provide the water supply in a sustainable manner. So basically, uh, so in order to understand the in and outs of these systems and to see how we can basically reach this sustainability and make use of high flood period to store this water and reduce this deficit during the summertime, we need to characterize these karst systems, especially in poorly investigated areas where we're doing our research in Lebanon, the Middle East, and the Mediterranean region. So the research question that one asks themselves is basically, how can I be able to delineate the complex catchment area of a karst spring? So where is this point that contributes to the spring, and where is this point that does not contribute to the spring? And that has implication on pollution and on water balance. What is the relationship in karst between rivers and springs? If we have very polluted rivers and less polluted springs, what is the implication of this relationship on water quality, and how we can depict it actually? How can we define transport processes and parameters in karst systems? How is it possible to evaluate some low indicators, some low cost indicator parameters for contamination instead of measuring very sophisticated parameters at the spring? So these are all questions that we ask ourselves. We have only scratched the surface. I mean, as far as the work we have been doing so far. But I mean, these are open questions that remain. So if I can just call this characterization methods, I call it from monitoring to modeling. So we gather some data, we try to conceptualize a system, and we try to put all of this data in a model, so that, I mean, at least this model represents some decision tool for local stakeholders or for us as scientists as well. So the monitoring, I'm just going to show a couple of pictures in the field where we collect some high resolution data on spring and climate, where we do some geological and surface characterization, both in the office, and we validated in the field. Tracer experiments for various reasons. We use also some environmental tracers to estimate groundwater age. And finally, we also do some hydrochemical sampling of persistent micropollutants. For instance, these are the new trend, but we use them as transport indicators. So a couple of pictures. This is just to show the importance of high resolution data and monitoring in areas that are poorly investigated. Without that, and without the acquisition of high resolution chemographs and hydrographs, it is very difficult to understand the functioning of the Karst system, especially that it is highly responsive to precipitation events. So climate, springs, soil moisture. Also, we do some interesting work in the field where we measure flow rates in springs using both physical methods and empirical methods. We developed some dashboards for the transmission of real-time data that we hope to use later on in some early warning system, if possible. Then the geological characterization of sites. This is very, very important because, as I said, Karst systems are very complex, and not what I mean. The things that are visible outside on the surface are nothing compared to what is hidden in the subsurface. And sometimes we have the chance to have very well investigated sites, and some other times, unfortunately, it is very, very difficult to characterize something in the subsurface. So we try to rely on the bits and pieces of knowledge that we see on the surface to dig deeper on what lies in the subsurface. So here you can see the mapping of dough lines could tell us, could give us an idea about the preferential flow in the subsurface, etc. So tracer experiments are very, very important, and we use them in Karst to assess fast transport parameters. So here, for instance, we injected a tracer in the river, and the tracer was very well diluted, and then it appeared in the spring. And this is a very polluted river that is unfortunately polluting the spring as well. So basically, other types of parameters that we seek in Karst systems, since tracer experiments allow us to retrieve velocity, fast velocity rates, environmental tracers will give us an idea about the estimation of average groundwater ages. For instance, if we use tritium, helium, tritium, CFCs, SF6, etc., this will allow us to have another perspective of the ages in Karst. Hydrochemical methods, for instance, we use micropollutants as transport indicators, and this allows us to know the origin of the infiltration, and will allow us also to know the loads. And actually the loads can be traced back to the source of contamination. So we're talking here about micropollutants, indicators of hospital waste or domestic waste, etc. So these indicator parameters are actually very important, because if we find this relationship between micropollutants and a certain low-cost parameter that we can measure at the spring, we are able basically to use it as an indicator for a certain contamination. So, for instance, turbidity has proven to be a very good indicator of contamination, but still we need to investigate it case by case in the respective springs that we are looking at. Now, if we're looking from monitoring to modeling, after we have gathered all of this data, and believe me, I mean, there is never enough data to be able to construct a model, we try to develop some models or to apply some models depending on the level of data that we have. So we can do some statistical analysis of time series. So this allows us to understand the functioning of a system. I'll show some examples right now. We can do some 1D and 3D transport modeling whenever possible. And finally, depending also on the site, we can develop some lumped or distributed numerical model and do some sensitivity analysis on them to reduce their uncertainties. So So the research questions here and the application of this side of the talk is basically, can we transform any conceptual hydrogeological model into an integrated numerical model? And can we use this integrated numerical model as a decision support tool for future prediction? So this is a question that we asked ourselves. And another one is basically, what is the sensitivity of the model output that we have? Is our model highly uncertain? How can we reduce the uncertainty? And did I use the right model? So given the level of data that we have, did I apply the right model? These are questions that, uh, I mean, the entire Karst community, especially those dealing with Karst modeling, are asking themselves. And finally, how to apply our knowledge of flow and transport, for instance, in developing early warning systems to overcome flooding likelihoods or to overcome any potential contamination that may occur. So in other terms, we can, if we have tackled those aspects, we can eventually answer the questions. If I were to have contamination, when will the pollutants arrive? First at the spring. What are the maximum concentration that I'm expecting, and what is the duration of the breakthrough of my contaminant at the spring? So if we are able to answer these questions in Karst, then we have we have succeeded in protecting this source, this resource at the source. So an example of 1D transport modeling, we use tracer breakthrough curves, as you can see here, to come up with transport parameters. And these are even varying under different flow conditions. So it allows us to have transit times, for instance, for the transport of a certain conservative contaminant. Sometimes an injection of a tracer under the snow allows us to see what is the response of snow melt onto a flow. Actually, we have a project called Snow Flow. So, and this is investigating specifically this aspect of snow-governed catchment areas. The time series analysis of chemographs, as you can see here, we're analyzing events after precipitation. This allows us to understand the infiltration origin. Where is this pollutant coming from? And whether this is a diffuse source or a rapid source or a fast infiltration source, and also mass loads. Time series analysis of hydrographs gives us insights into the complexity of a system. So it allows us to understand something about Karst typology. For instance, whether the system is highly responsive, whether we have slow, fast flow functions, whether we have significant storage, and this has an implication on water sustainability as well. Finally, the modeling, I mean, we can use linear reservoirs, what we call lump models, where especially when we don't know a lot of information about the subsurface, or when the subsurface is very, very complex, or if we can model the system using an equivalent porous medium, then we can use a distributed integrated numerical model. And as you can see here, this model allows us to translate the precipitation input into an output that is a discharge at the spring. So this is an example of an output. So, and but again, this one question remains: what is the most suitable model to use? We don't want to overestimate, we don't want to underestimate, and this is a very big question that remains. Finally, a model as a decision tool. We can use a model as to predict the flow of water under climate scenarios. I'm gonna just briefly show the diagram, and then we can use a model also with its sensitivity analysis as an application to quantitative vulnerability. So what are the parameters that play a role effectively in recharge and in contamination? And these should be investigated investigated further and taken in great details when we're discussing vulnerability of a system. So take-home messages, basically, it is very important to have a well-monitored site and to work on pilot areas. This is my opinion, especially in poorly investigated sites of the Middle East and particularly in Lebanon. And high-resolution data are very, very important. And also there's a big need of characterization of flow and transport of Karst because they do not function the same way any other porous media functions. And the beautiful thing about it is that we have a multitude of methods going from chemistry to physics and math that allow us to develop methods for characterization of these two characteristics in Karst. So another take-home message, it is important to apply a numerical model in order to understand our water resources and to have this decision support tool. It is very important if we, again, know the right model to apply. And basically, if we are able to decrease the uncertainty given the characterization of flow and transport that we have of our systems. So basically, that's my talk. Thank you. Thank you for inviting me.
So thank you very much, Joanna, for sharing your talk, your research, and most importantly, your passion for groundwater. It was a real pleasure to have you in the Water Underground talks.
Thank you for the opportunity, Viviana. Thank you very much. It was a pleasure equally. Thank you.